This video is meant to give a little bit of background about some of the exercises and problems in Chapter 3. The first exercise asks, in what way does the string of a bow and arrow behave like a spring? Well, as you draw a string away from its equilibrium position, which would be this straight up and down in this bow, right? So it'd be straight up and down, if you could draw straight anyway. As you draw it away from this equilibrium shape, there's a restoring force that it experienced that's proportional to its displacement, to how far you pull it. So it's acting just like a spring. Interestingly, Peter Heather, in his book The Fall of the Roman Empire, makes the case that it was the recurve bow. This was a new type of bow that was originally developed, in one place at least, by the Scythians. And this type of bow, look, it has two curves in it, the traditional and then sort of a back curve right here. This recurve bow allowed the Huns to shoot their arrows a few meters further. This allowed them to encroach on the territory of others. These individuals in turn pushed on the Roman Empire, and so that's why Heather makes the case that the fall of the Roman Empire, in essence, can come back to the technological innovation of the recurve bow. Question 4 asks, when you lie on a spring mattress, it pushes most strongly in the parts of you that stick into it the furthest. So it would be like the part of you that pushed in, and this is your hip, say. So the mattress would be pushing up on your hip harder than it would be pushing up on some part of your body that was not pushing in so deeply. Why doesn't it push up evenly on your entire body? And the answer to that is that the deeper you dent this mattress's surface at any given point, the stronger the local restoring point becomes. So that's why it doesn't push up evenly on the entire body. Question 5 asks, if you pull down on the basket of a hanging grocery store scale so it reads 15 newtons, how much downward force are you exerting on the basket? The trick about this problem is it's so easy that you tend to fool yourself. Okay, I've just put a 15 newtons. See the 15 here? I'll change it to 10, and now I'll change it back to 15. Okay, so I've got a 15 newton weight. Those are the weights right there. I'm going to start weighing. Okay, now weighs 15 newtons. It bobbles around a little bit. That means it's pulling down with a force of 15 newtons, right? So it's simple. In fact, it's so simple it fools you. Let's try, we're going to reset it. Let's try 10 newtons. Okay, so we're going to try 10 newtons. Well, there we go. We're pulling down with a force of 10 newtons. Question 14 asks, steep mountain roads often have emergency ramps for trucks with failed brakes. I've often seen these out west. Why are these ramps most effective when they are covered with deep, soft sand? Well, the answer is the sand dents easily as the truck plows through it and extracts energy from the truck. So the truck does work in pushing the sand out of the way. The sand converts that work into safe thermal energy. Let's see what happens when this doesn't quite work the way we think it should.
Carbon County, Pennsylvania. TV news cameraman Rob Gill sets up on the side of a highway, shooting a report on an unsafe runaway truck ramp.
There was several truck accidents on this ramp before, and trucks would come and flip. So I was just getting some general shots of the truck ramp.
But less than 3 minutes after Rob arrives, this minor story becomes breaking news. gravel should slow the truck, but the truck vaults off the first mound. The second row is like a wall.
I was looking through the camera the whole time. I had no idea that the back end of the truck was going to go into the air like that.
The driver stumbles out, dazed and stunned by the violent crash.
Okay, now back to question 16. So this one asks, during rehabilitation after hand surgery, patients are often asked to squeeze and knead putty to strengthen their muscles. How does the energy transfer in squeezing putty differ from that of squeezing a rubber ball? Well, that one's pretty straightforward. Energy transferred while you're deforming putty, here's the putty right here, is converted into thermal energy. It never returns to that person's hand. But the energy transferred when you're deforming a rubber ball becomes elastic potential energy in the ball, and it returns to that person's hand when the rubber ball returns to its spherical shape. So you're getting a little energy back if you have that elasticity. Physicians prefer that you work a little harder, so they don't want you to have that elastic ball. Question 25 asks, why must the surface of a hammer be very hard and stiff for it to drive a nail into the wood? And the answer is simply the force that the hammer exerts on the nail during their collision would diminish if the hammer's surface distorted very easily. So if this bent very easily, you wouldn't get as much force out there. Question 31 asks, railway tracks must make only gradual curves to prevent trains from derailing at high speeds. Why is a train likely to derail if it encounters a sharp turn while it's traveling fast? Well, remember, the acceleration needed to keep something going in a circular motion is equal to v squared over r, right? So you can imagine this is sort of the circle center right there. There's your r. The faster you're going, the smaller the radius. Overall, the bigger the acceleration needed. Force is equal to the mass times the acceleration. If this acceleration's big, right, that you need to push it, keep it pushed and going around in a circular motion, multiply that by the mass of the locomotive, the force needed is tremendous. And so if you don't have it, if you're going too fast, disaster. A salad spinner is a rotating basket that dries a salad after washing. How does the spinner extract the water? Well, essentially, what's going on is, okay, here's your salad spinner. There's a picture of one right there. That's just like the one I have at home. And so if you're looking straight down on it, as you put your lettuce inside and you spin it, the water wants to keep going straight, actually, and it sluices right through that little colander right there, and so the water dribbles out the sides and you've got your lettuce all nicely dried off. We can take a look at that right now.
Hi, I'm Yvette, and one of the most essential tools in my kitchen is my OXO salad spinner because I love making salads. I've tried other salad spinners, but I've found the strings and crates a bit awkward and difficult to use. This OXO salad spinner was actually inspired by a top during a trip to the toy store. Let me show you how it works. First, you wash your lettuce directly in the basket. For really gritty spinach or arugula, you can even use the bowl to soak your greens to get all the sand off, and the basket doubles as a colander. Next, place the basket back in the bowl and secure the lid on top. Here comes the fun part. You just give the spinner a few pumps to get it going. I do this a couple times to make sure all the water comes out. Once all the water is out, just press the brake right here on top and it stops automatically. Now, all the water's on the bottom of the bowl. You can even use this bowl to serve your salad or store it in the fridge. And when you're done, cleanup is a snap. You can easily take apart the lid, and the basket, bowl, and lid are all dishwasher safe on the top rack.
Now let's go to a couple of the problems. First, it asks, your new designer chair has an S-shaped tubular frame, so it looks like this one I've shown right here. When your friend who weighs 600 newtons sits on the chair, it bends downward by 4 centimeters. So what's the spring constant for the chair? Well, we'll just say that, let's see, 4 centimeters is the equivalent of 0.04 meters, right? So then we can say, remember, F is equal to, well, it's minus kx, but we're going to ignore that that minus sign right there, because it simply means it's a restoring force, and we just want to solve for the absolute value of this k. So we'll just say force over distance is equal to k, and so in this case it's going to be 600 newtons divided by 0.04 meters, and so we'll have 15,000 newtons per meter. That's our spring constant right there. So now it asks for part 2, or number 2, you have a friend who weighs 1,000 newtons. When this friend sits on the same chair, how far does it bend? Well, we essentially have already worked out what k is, and we're told what the new f is, and so we can insert those values. So I'm going to ignore the minus sign, okay, because we know that just means it's a restoring force. So we'll say 1,000 newtons is equal to 15,000 newtons per meter times whatever that distance that it goes down. So now all we have to do is solve. So we divide both sides by 15,000 newtons per meter, 15,000 newtons per meter, and you can see the newtons cancel, the meters comes back up, and then when we work that out, it turns out that x is equal to 0.067 meters. If you want to, you can translate that into centimeters, which is 6.7 centimeters.